Hello. In the previous videos of current electricity, you have learnt about the EMF and the potential difference. Now, in this video, you will learn about internal resistance of a cell and then the combination of cells in series and parallel combination. Internal resistance of a cell is the resistance offered by the electrolyte of a cell to the flow of current between its electrodes. And the internal resistance of a cell depends upon nature of electrolyte and directly proportional to the concentration of the electrolyte, directly proportional to the distance between the electrodes, inversely as the common area of the electrodes immersed in the electrolyte, and it increases with decrease in temperature. Let's derive a relation between internal resistance EMF and terminal potential difference of a cell. For this, consider a cell of EMF E and internal resistance small r connected to an external resistance capital R as shown, and suppose a constant current I flows through this circuit. So by definition of EMF, E will be equal to work done by the cell in carrying a unit charge along the closed circuit, and that will be equal to work done in carrying a unit charge through the external resistance R plus work done in carrying a unit charge against internal resistance small r, and that will be denoted by capital V and small v. So E will be equals to V plus small v, and by Ohm's law, capital V will be equals to I into capital R and small v will be equals to I into small r. So from here you can see that the value of I will be equals to E divided by capital R plus small r. Internal resistance of a cell in terms of E, V and R. Again, by using the same equation, E is equals to V plus V dash. Only difference is in that slide, instead of V dash, it was simple V. From here, I into small r will be equals to E minus V and divided by capital V on the right side, and on the left side put the value of capital V equals to IR. You got the required relation. Small r is equals to E by V minus 1 into capital R. Now, grouping of cells. Because from a single cell, you can take the value of only that much potential or EMF from the cell, which one is equals to, for a normal cell it is 1.5 volts. You used in a torch 2 or 3 cells, right? And next time whenever you will fill the cells in the torch, just note the method how you are using the cells. Let's understand firstly the combinations, then we will come to this example again. Now, in the grouping of cell, why we need? Because a limited amount of current can be drawn from a single cell or battery. And if we want to use the value of potential more than that of a one cell, then obviously I have to use the combination. Firstly, the series combination. See, the diagram clearly shows that there are two cells E1 and E2, EMFs and internal resistances R1 and R2, and they are joined in the series combination through the external resistor capital R. Now, how you can check that this one is a series combination? The first cell's negative terminal is connected to the positive of the next cell. And similarly, if there are three cells, then the second cell negative will be connected to the third cell positive. Then such type of combination is known as series combination. Points A and B in the circuit shown in the last slide of the video acts as the two terminals of the combination, and if we combine the two cells, then you can redraw the circuit diagram as shown in this slide, that simply E and small r. Here this will represent the combination of the internal resistances R1 and R2, and E represents the E equivalent. Let's derive this. Apply the Kirchhoff's loop rule to the diagram shown in the last slide of the video, and you will get the current I is equals to E1 plus E2 by R plus small r1 plus small r2, and this shows that the internal resistance combination R equivalent will be equals to R1 plus R2 and E will be equals to E1 plus E2. Now, cells in the series combination, let's summarize that. There are three cells having EMF E and internal resistance small r each, connected to the capital R external resistance, and the current I flows through the circuit. So, as we have calculated that the equivalent EMF will be the sum of E1 plus E2. Now here it will be E1 plus E2 plus E3, and as all the cells have same EMF, so it will be 3E. And similarly, the internal resistance will be 3 into small r. So in general, if there are n cells, then the total EMF of the battery formed will be n into E. And this one is the combination which you use in the torch. The internal resistance will become n into small r. The total resistance of the circuit will be n into r plus capital R. And the current will be n capital E upon n into small r, means the total internal resistance plus the external resistance. And when internal resistance is negligible in comparison to the external resistance, then by putting in the formula of current, you can see that the cells are connected in series to get maximum current. Now let's move to the next combination, parallel combination of cells. Here in the diagram, the two cells having EMFs E1 and E2 and internal resistances R1 and R2 are in parallel combination. Parallel combination means their positive points, positive terminals are connected to one common point and the negative terminals are connected to the another common point. So by applying the Kirchhoff law in the loop containing E1 and R1, and again in the loop containing E2, R2 and capital R, you got these two equations, and on solving these you will get the value of current. And by rewriting the value of current, you can find out that capital E is equals to E1 R2 plus E2 R1 upon R1 plus R2, and therefore the equivalent EMF will be equals to this one, and the equivalent internal resistance will be R1 R2 upon R1 plus R2, or you can say that the parallel combination resistance, as we have derived earlier also, 1 by Rp will be equals to 1 by R1 plus 1 by R2. Let's generalize the formula for cells in parallel combination. In the diagram, there are three cells of same EMF E and internal resistance small r connected in the parallel combination, and as calculated, the total EMF of the battery will be E, internal resistance will be R by N, and total resistance of the cell will be R by N plus capital R, because this one is in series combination to that total circuit. And the I current will be equals to NE upon N capital R plus small r. And the external resistance is negligible in comparison to the internal resistance, then the cells are connected in parallel to get maximum current. In the numerical problems, instead of E and small r, either in series combination or in parallel combination, there will be values given to you, and you have to put those values and find out the value of current flowing in the circuit. Or in some another numerical problems, there may be the combination of cells, means as we have done in the resistances, there may be two cells in the series, and then that series combination may be connected to the combination of cells in parallel, and you have to solve that. Means in a numerical problem, there may be a combination of cells in series as well as in parallel. So just by following the rules you have studied here, you can solve the numerical problem given in your book. Thank you.